In this section, we're going to talk all about energy. So we're going to look at what constitutes energy, and when we think about energy and reactions, are we looking at a system, are we looking at a surroundings, or are we considering the rest of the universe? We'll also start to think about the laws of thermodynamics. All right, so to start off with, we need to think about the flow of energy. All right, so we're always going to travel to or from something. And so usually what we're looking at in chemistry is we're looking at some sort of reaction system. So that's going to be our reference point. So our energy is always going to go into or out of our system, into or out of our surroundings. Okay, so our system, that's the part of the surround universe that we care about. Whether I'm doing my reaction in a beaker or a flask or things like that. The surroundings, technically speaking, are the rest of the universe. But when we think about the direct surroundings, we're looking at what's directly around the system. Because we've got our system, like let's say this container right here is my system. My surroundings are going to be what's directly around it. So I'm in a room right now. Let's say my garage on the other side of my house through several doors. Okay, that would be the rest of the universe. That's not the direct surroundings of my particular experiment, because that's all the way somewhere else. When you're in a lab, your system is whatever you're looking at, and your surroundings are what, the environment in your lab room, and then the rest of the universe, once you leave your lab, that would be the rest of the universe. So when we think about energy, we can think about things like kinetic energy. So kinetic energy is our energy of motion. Okay, we can also think of energy in terms of thermal energy when we take a temperature of something. Thermal energy is just simply kinetic energy. All right, and so our kinetic energy is 1/2 the mass times the velocity squared. I've got a nerdy little cartoon here. In this cartoon, this kid and his sister, they're on a roller coaster, and so the kid, he's a complete nerd, and so he has his calculator on the roller coaster trying to calculate the energy from the roller coaster. An easier thing maybe to think about is if we have like a pool table and we have a cue ball, and our cue ball comes in and it hits a ball, okay, work is done on the other ball by the cue ball. All right, and so we transfer that energy, and then we get that kinetic energy, our energy due to motion. We have a few different units that we consider: the joule, the calorie, the kilocalorie, and the capital C calorie. All right, this can be kind of confusing. You have to pay attention to capitalization. And if you look at the kilocalorie and the calorie, so if you look at these two right here, you'll notice that they're the same. Okay, so a kilocalorie is just 1,000 times a lowercase c calorie, and then we've got our capital C calorie. When you look at food labels, pay attention to whether or not it's a lowercase or a capital calorie. Okay, again, remember our joules, we've got that kilogram meter squared times second squared. When we think about heat, all right, for heat, we're going to use this variable right here, this Q. Okay, so that's our energy that we're looking at between a system and surroundings due to differences in temperature. This is our thermal energy. And again, it's a measure of kinetic energy. So I'm going to try a really bad drawing here. All right, but let's say, we have a thermometer bulb here that has, that red alcohol in it. Okay, so something is going to come along and keep hitting our thermometer bulb. All right, so I've got my thermometer suspended in some sort of solution or air or something, and there's particles, and those particles are going to keep hitting that thermometer bulb. And so the more frequently they hit, right, that higher that temperature is going to be. And so if they're continuing to hit, the little alcohol, and our thermometer continues to go up. Okay? All right, and then our other variable here that we're looking at right now is work, and that's that energy that's transferred when that object's moved by a force. So that cue ball hits the other ball, and it does work on it, and it causes the other ball to move. Okay? So When we think about energy, we need to start understanding the laws of thermodynamics. All right, so this now brings us to the first law of thermodynamics, which is the main one that we're going to consider in a first semester level general chemistry course. If you are taking a second semester general chemistry course, then you'll talk more about the second and third laws of thermodynamics. But the main one that we're concerned with at this level is our first law of thermodynamics. So think about it. Maybe you've heard about it in another class. Maybe you've taken a physics class where you've learned some of the laws of thermodynamics. Okay? So our first law of thermodynamics says that the total energy of our universe is constant. All right, so energy can neither be created nor destroyed. So we call this the law of conservation of energy. It's neither created nor destroyed. It's just transferred. And it looks like this. Okay, the delta E of the universe, the change in energy of the universe, is equal to how our system changes and how our surrounding changes. And so that has to equal 0. And so we have an equal and opposite type of interaction happening here. If my system gains energy, my surroundings have to lose energy. If my system loses energy, my surroundings gain energy because they have to cancel each other out to get to 0. All right? So whatever one does on the other, that gets the opposite. Okay? So, because we've got a system with energy E. If no energy could enter or leave a system, then the change in the energy would be 0 because energy is conserved, all right? And so we have to have that opposite. So, if, I've got plus 143 kilojoules is the delta E of my system, then I have to have a negative 143 kilojoules for the delta E of my surroundings, because that would give me 0, and that's the delta E of the universe. All right? So energy is neither created nor destroyed. All right, so when we look at the flow of energy, we know that the change in something, we typically look at the final minus the initial. So when I have a reaction, okay, my reaction goes reactants to products. Didn't quite give myself enough room to write there. All right, and so my products are my final state, and my reactants are my initial state. So when I look at my flow of energy, okay, I get my energy of my products minus the energy of my reactants is my delta E. Okay, now we have two things that can happen. My system can give off energy to the surroundings, or my system can take in energy from surroundings. And this is where we start differentiating between what we call an exothermic and an endothermic reaction. An exothermic reaction gives off energy. An endothermic reaction takes in energy. So exo, outside, gives it off to the outside. Endo, inside, takes it in into itself. Okay? So take a look at these two diagrams here. Which one do you think is the exothermic diagram, A or B? Well, if you said A, you were correct because energy is being lost to the surroundings in A. All right, so this is our exothermic. Okay, which means that the energy gained from surroundings into the system, this needs to be our endothermic. Okay, and so the energy of the system is going to decrease in A, and the energy of the system is going to increase in my picture B. And so let's think of this here. For that exothermic, what do you think delta E is going to end up being? Is delta E going to be positive or negative? Delta E is going to be negative, which means the delta E over here is going to be positive. Okay? So to give you another look at it, here is that same thing if you think about water, okay? So I made some tea earlier. So my water was hot. When I put my hands around the cup was nice and warm because the tea in the cup, that is my system, and my hands are the surrounding. And that can be kind of the difficult part with this, is you have to think that you are the surroundings. This is the system, okay? And so what you're perceiving is what's happening as the system either gives something off or takes something in. So if you are feeling heat, that means the system is giving off the heat, all right? And if you put your hand around something and it's super cold, that means that the system is taking in energy from the surroundings, all right? So this is going to be our exothermic. So as your hot water is cooling down, and then this is going to be your endothermic here. All right, as that water with ice in it cools down, or warms up, I mean. As the water with ice in it warms up to room temperature, okay? All right, so here's another one. Again, delta E of the system is negative. This is your exothermic. Your surroundings gain energy. And then here, the delta E of the system is positive. Your surroundings is negative. This is your endothermic. Okay, so that is our flow of energy. Okay, so again, you can think of the box in this picture as kind of like if you work in a fume hood, is kind of like your fume hood. All right, and so if energy leaves the system, it gets a negative, and if energy enters the system, it gets a positive. Now, when we look at heat and work, if both heat and work are positive, our delta E will be positive. If both heat and work are negative, our delta E will be negative. But if they're opposite signs, it's just going to depend on how big either of them are when you put them together. So if Q, a positive sign means the system is gaining heat, negative means it's losing heat, and W, positive means work is being done on the system, negative means the work being done by the system because it's giving off. All right, so take a look here. All right, so I have a couple of diagrams here. So right here, these are the initial conditions. Okay, and then these over here, these are the possible final conditions. So looking at the initial conditions and the possible final conditions, can you figure out which one of the three possible final conditions is the correct one? All right, so we're saying that the delta E of the system is negative. All right, so that means that our system needs to lose energy and our surroundings need to gain energy. So system okay, so is there one that we can rule out right away? Yeah, if you said C, that is correct because the system goes up energy and the surroundings go down. Okay, so we're going to rule out C. Okay, that leaves A and B. Well, if I look at A, my system lost energy because we started off at 3 ticks and now we're down to 2. And B, we also lost energy. Okay, so those look good so far. Now, when I look at my surroundings, now remember the delta E of the universe needs to be 0. So the change in one needs to be the opposite change in the other. So if my system lost a tick of energy, my surroundings need to gain a tick of energy. So between A and B, which one is that? Yeah, it's A. Okay? All right, so here's an example where we've got some gasoline in a car engine. All right, we're doing combustion. We've got carbon dioxide and water vapor. They expand, which pushes pistons. We have excess heat being removed by a cooling system. So my expanding gases are going to do 451 joules of work on the pistons, and the system is going to lose 325 joules to the surroundings. We want to calculate our change in energy in joules, kilojoules, and kilocalories. Okay, So my problem says that the expanding gases do work. Okay, so that means that my system is negative. So we get negative 451 joules. Okay, and then it says that the system loses energy. So if my system's losing energy, that is also negative. So that would be negative 325 joules. Okay, and so my delta E, I can take my heat plus my work. So I'm going to get negative 325 joules plus negative 451 joules. And so I'm going to get negative 776 joules. Okay? So my total change in energy there between the work and the heat is negative 776 joules. All right, we also wanted kilojoules and kilocalories. So we're going to take our negative 776 joules. We get a kilojoule for every 1,000 joules, and so we get negative 0.776 joules. All right, 1 kilocalorie, as shown in an earlier slide, is equal to 4,184 joules. All right, so we're going to get negative 776 joules times 1 kilocalorie and 4,184 joules, and that's going to give us negative 0.185 kilocalories. Okay? All right, now, one last thing on energy. I want you to think about where all the energy comes from, because when we're talking chemical reactions, we're not really talking about gases expanding and pushing on pistons. We're talking about what's happening on a molecular level with our reactants and our products. And so we need to understand that there's a lot of energy associated inside of that. And so when I look here, I can see that I get a lot of different components of energy. Okay? Contributions to kinetic energy are going to come from my molecules moving around. That's the translation. Okay, my molecules rotating. Okay, vibration. So here's the thing. When we do molecular models, we use these ball and stick systems where we've got a ball, we have a little plastic stick, and we have another ball. And it seems pretty rigid. But in reality, bonds are not like that. Bonds are actually really like stretchy. And so we get this vibrational energy, okay, where they bounce. Okay, they bounce. So they're not like this perfect stick. And then we get kinetic energy from our electrons, all right? Hopefully you remember from prep chem that you learned, you know, when we think about the structure of an atom, we like the Bohr model because it's very visual for quantized energy levels. However, we know that that's not exactly how electrons are presented in an atom. They're bouncing around everywhere. So our electrons are moving around. So that's all contributions to kinetic energy. And when we start looking more at energy, those bonds, well, we get energy usually from forming them, and then it takes energy to break them apart. And so we get potential energy where, you know, the amount that something vibrates, that's a potential amount of energy. And then we've got, you know, within our atom, even in the nucleus, all right? So actually, unless we're at absolute zero, which we've never managed to get anything to absolute zero is the cessation of all motion completely whatsoever. So we've never managed to get all the way to absolute zero because even the protons and neutrons inside of a nucleus, they have itsy bitsy teeny tiny amounts of vibration in them. All right. And then we get potential energy from the bond. And so that's where, you know, once I have something bonded together, there's potential energy there because it's either going to take energy to break it apart or to form that bond, there's potential energy for the formation of the bond. And so there's all sorts of things at play when we think about the energy associated with our various different reactions.